Hello class. Today's lecture examines the intellectual scaffolding that undergirds modern health informatics. As Ramona Nelson reminds us, nothing is as useful as a good theory to guide the process. Our goal is to trace the pathway from foundational technology-related literacies to the grand, middle range, and micro theories that shape design, implementation, and evaluation of informatics solutions. By the end of this session, you should be able to 1. Explain the major technology-related literacies and their relevance to informatics practice. 2. Differentiate how theories and models function within the informatics domain. 3. Describe systems theory's core components and its importance for managing complexity. 4. Discuss information theory constructs, particularly the data, information, knowledge, and wisdom continuum. 5. Assess the role of planned change through diffusion of innovation and related change theories. And last but not least, apply the Staggers and Nelson Systems Life Cycle Model to real-world informatics projects. Welcome to our healthcare management videocast. This chapter provides an overview of technology-related literacies, theories, and models useful for guiding practice in health informatics. For both providers and patients, developing knowledge and related skills in health informatics first requires a foundation in technology-related literacies. Please look at the figure in the slide for a second. So now imagine literacy as stacked, interlocking layers. At the base is basic literacy, the ability to read, write, and comprehend language. One level up sits computer fluency, the hands-on know-how to navigate hardware and software with confidence. Beside it is information literacy, the set of integrated abilities encompassing the reflective discovery of information, the understanding of how information is produced and valued, and the use of information in creating new knowledge while participating ethically in communities of learning. When computer fluency and information literacy merge, they form digital literacy, the capacity to locate, evaluate, create, and communicate content via digital tools. Floating over this strata is health literacy, because every encounter in care, from reading prescription labels to interpreting portal messages, depends on understanding health concepts. Where the digital and health layers intersect, we arrive at digital health literacy, the ability to search, appraise, and apply electronic health information found in patient portals, telehealth visits, and wearable dashboards. Note the red ellipse on the slide. It spotlights the overlap between computer fluency and information literacy, reminding us that neither coding prowess nor database searching alone is sufficient. Clinicians must translate raw data into meaningful insights, and patients must judge the credibility of online advice before acting. As we progress through the course, we'll revisit each literacy and connect it to frameworks that illustrate how mastery of every layer shapes adoption, safety, and equity in health IT initiatives. Our learning objective for this slide, the role of theories and models, is to describe how different kinds of theories relate to the models we use in everyday informatics work. Now, think of a theory as an explanatory engine. It tells us why a phenomenon occurs and how its parts fit together. Because phenomena vary in complexity, theories come in 3 sizes. Grand theories tackle broad, multifaceted experiences, say, a comprehensive theory of human learning. They are conceptually rich but hard to test directly. Middle-range theories focus on a single, patterned event, such as how people adapt to organizational change. They are specific enough to study rigorously, yet abstract enough to generalize. Micro-theories focus on one tightly bounded situation. For example, staff reactions during the first month of a new electronic health record rollout and are now easier to test thanks to web 2.0 analytics and meta-analysis. Theories evolve through a recursive cycle. We observe a phenomenon, propose ideas, map key concepts into a conceptual framework, and refine that framework until a coherent, testable theory emerges. Evidence then accumulates, and the theory is revised, rejected, or accepted. A model is the visual equivalent of that narrative, a diagram that shows the concepts, arrows, and feedback loops, allowing clinicians and IT teams to see the moving parts at a glance. Models can portray anything from a standalone theory to a multi-theory framework. Because informatics problems sit at the crossroads of medicine, computer science, and social science, most of our models are really theoretical frameworks that braid together ideas from several middle-range or micro-theories. One theory undergirding all these constructs is general systems theory, the view that people, tasks, technologies, and environments form an interdependent whole. You'll see that lens applied throughout the textbook, especially in Chapter 2, which unpacks each framework listed here in depth. By pairing robust theories with clear visual models, we gain a shared language for predicting adoption, troubleshooting failure points, and ultimately designing safer and more innovative health information systems. So now in this slide, picture any clinical setting. Patients arrive, data flow through monitors, orders trigger pharmacy fields, and outcomes loop back to care teams. That whole constellation is a system, a set of related interacting parts contained by some boundary, the hospital, the care pathway, or even the patient's body. In informatics, we are most concerned with the open systems. Their boundaries are semi-permeable, allowing them to exchange information, matter, and energy with the outside world. Your electronic medical records, for instance, ingest lab results, input, process them into dashboards, throughput, and send alerts to nurses, output. Those alerts, in turn, generate new notes and orders, feedback, that re-enter the system. A closed system, one sealed off from its environment, almost never exists in healthcare because isolation defeats care coordination. Open systems share three core characteristics: purpose, the why. Every system aims at a goal. For a sepsis alert algorithm, the primary objective is to facilitate early detection and intervention. Purpose gives the system direction and a yardstick for success. Structure, the what? This is the anatomy, people, software, devices, policies, and the boundary that holds them together. Mapping the structure, often with a swim lane or data flow diagrams, reveals where breakdowns or bottlenecks may lurk. Functions, the how. These are the processes that transform inputs into valuable outputs. In a telehealth platform, functions include triage routine, video consultation, documentation, and billing. Why does this matter for you as a healthcare manager? Systems thinking enables you to trace adverse events back to structural gaps, redesign workflows to realign purpose and function, and identify unintended consequences before they propagate through feedback loops. It is the scaffolding beneath every socio-technical adoption or evaluation model you'll meet in Chapter 2 of the textbook, and the conceptual glue that ties informatics to patient safety, quality improvement, and strategic planning. As we delve into subsequent frameworks, recall this slide: inputs, processes, outputs, and feedback operating within purposeful, structured, and open systems. Master that rhythm, and you'll manage technology change with far greater clarity and control. In this slide, the open system interacting with the environment is the heartbeat of every informatics intervention, from a bedside monitor to a national health information exchange. The dashed oval marks the system boundary. Everything inside is the working lab. Everything outside is the external environment. regulators, vendors, public health, even weather events affecting power or bandwidth. Input. On the left, the arrow entering the boundary reminds us that open systems never start empty. We draw in information, lab feeds, patient-generated data, matter, supplies, medications, and energy, staff effort, electricity. In analytics projects, the matter might be HL7 messages, and the energy is server time. Process. The dashed box in the center is where transformation occurs. Algorithms flag a rise in creatinine, nurses interpret the results, and providers adjust the care plan. This is the system's value creation zone. Mapping these steps enables managers to identify redundancies and automate processes wisely. Output. On the right, the arrow exiting the boundary shows the products we send back: a clinical decision support alert, a discharge summary, a replenished inventory, even a healthier patient. Notice that the output mirrors the trilogy of input: information, matter, and energy. Feedback loop. The heavy arrow curving beneath completes the circuit. Outputs don't vanish. They re-enter as feedback, reshaping subsequent inputs and processes. Think about an early warning score dashboard. Every correction you make today alters tomorrow's risk profile, which then feeds the algorithm anew. Why highlight this diagram? Because every breakdown you'll troubleshoot traces to a misaligned element here. Dirty inputs, opaque processing, delayed outputs, or, most commonly, missing feedback. Systems theory trains us to diagnose the relationship between parts, not just the parts themselves. As you move through Chapter 2, keep this open system loop in mind. It's the Rosetta Stone that turns isolated data points into actionable, sustainable change in healthcare delivery. In this slide, information theories and models, we can see that the evolution of information thinking in health informatics begins with the Shannon-Weaver model, which frames communication as a linear flow: source, encoding, noisy channel, decoding, receiver, and feedback, highlighting the importance of reducing noise and maintaining feedback loops in today's data exchanges. Bloom's theory of information then clarifies how health-related signals become data once captured, information when organized for a purpose, and knowledge when they change clinical expectations, laying the groundwork for layered data warehouses. Graves and Corcoran extend this by situating data, information, and knowledge within the practice environment, emphasizing that context shapes every nursing decision. Nelson later adds wisdom as a stage where knowledge is applied to influence patient outcomes. Finally, the data information knowledge wisdom hierarchy encapsulates the entire progression, from raw data through contextualized information and synthesized knowledge to actionable wisdom, providing a practical checklist for any AI or clinical decision support project. Together, these 5 models trace a coherent storyline, from the mechanics of signal transmission to the semantics of meaning-making and the ethics of judgment, showing that practical informatics demands not just data velocity, but purposeful learning and wise action. In this slide, we can analyze how the Cynefin diagram helps leaders recognize which type of context they are actually operating in before they act, because cause and effect behavior differs in each domain. On the ordered side, a simple, sometimes called obvious, situation has clear, repeatable links between cause and effect. So the correct stance is to sense, categorize, respond, think, and follow the standard protocol, such as barcode scanning a medication. A complicated context is still ordered but requires expertise. The links exist, yet are not immediately apparent. Here we sense, analyze, and respond, just as a multidisciplinary team interprets conflicting lab values before choosing a treatment plan. Cross the dash boundary into the unordered world, and linear logic breaks down. In a complex setting such as introducing remote patient monitoring into a community, patterns emerge only in hindsight, so the adaptive move is to probe, run safe-to-fail experiments, sense, respond, and watch which solutions gain traction. A chaotic context, say a ransomware attack, disabling electronic health records, demands decisive action first. You act, sense, respond, stabilizing the situation before analyzing it. At the center sits disorder, the foggy state where we cannot yet determine which domain we are in. The remedy is to break the situation down into its components and assign each to the appropriate quadrant. By classifying problems in this way, informatics leaders avoid over-engineering simple tasks, under-analyzing complicated ones, or paralyzing responses in chaos, thereby matching decision-making methods to reality and improving both safety and agility. In this slide, we can analyze how change theory examines how individuals and organizations move from a current state to a desired future state, and two landmark perspectives illuminate that journey. Kurt Lewin's theory of planned change presents change as a three-step rhythm. First, unfreezing, in which leaders loosen the habits, assumptions, and routines that keep the status quo in place. Second, moving, when new behaviors, workflows, or technologies are introduced and actively practiced. And third, refreezing, when the new way becomes the usual way through reinforcement, policy, and cultural cues. Complementing this process lens, Everett Rogers' diffusion of innovation model focuses on who adopts a new idea and when. An innovation is first embraced by innovators who enjoy experimentation, then by early adopters who translate the novelty into practical advantages. Momentum builds as the early majority joins, tipping the system toward widespread use, followed by the more skeptical, late majority, and finally the laggards, who adopt only when the change is unavoidable. Successful transformation hinges on change agents, trusted individuals who bridge the gap between the innovation and its potential users, framing benefits, answering objections, and tailoring support to each adoption segment. In healthcare settings, understanding both Lewin stages and Rogers adopter categories enables managers to time communication, training, and reinforcement so that a new electronic health record, telehealth service, or workflow redesign moves smoothly from initial disruption to stable, value-adding routine. So now let's talk about the system's life cycle model. This slide shows the diagram of the system's life cycle as a spiral that never truly closes. It begins with analyze, where the organization assesses its environment, workflows, and readiness, identifying gaps and requirements. Insights flow into plan, the most labor-intensive stage, in which leaders decide whether to build, buy, or co-design a solution, map governance, and engage stakeholders. From there, the path splits into develop or purchase. Even when software is purchased, heavy tailoring and iterative co-design occur, feeding back to analysis and planning until a fit is confirmed. Once the product or configuration stabilizes, the project moves into the test phase, a standalone phase that stresses the system under near real-world conditions and triggers go or no-go decisions. A successful test leads to implementation, followed by the go-live period, during which training, command center support, and change management plans are executed. After go-live, the system enters a routine of maintain and evolve, where routine upgrades, new modules, and workflow refinements keep the technology aligned with changing clinical practice. Occasionally, a strategic pivot results in the installation and the start of a fresh spiral. Crucially, the dotted ring reminds us that context, culture, regulations, market forces surrounds every phase, so each action must be anchored in organizational reality. The arrows labeled Evaluate show that assessment is embedded in every step, not tacked on at the end. Metrics defined during planning are checked during development, retested during implementation, and revisited during maintenance. By depicting the life cycle as an expanding spiral rather than a closed circle, the model highlights that every completed project becomes the new baseline for future innovation, ensuring that health information systems grow with, rather than drag on, the organization they serve. Now, let's discuss complex adaptive systems, which are a living mosaic of autonomous yet interdependent agents, clinicians, patients, technologies, and workflows knitted together by countless feedback loops, allowing the whole organization to learn and adjust rather than simply react. Chaos theory reminds us that tiny variations, such as an overlooked allergy alert, can cascade into outsized outcomes, so linear root-cause logic is rarely enough. Complexity theory shows that order still emerges, best practice patterns and informal workarounds through self-organization at the edge of chaos, where flexibility and stability balance. The Cynefin framework then provides leaders with a practical compass, recognizing when care delivery is protocol-driven and straightforward, complicated and expert-heavy, complex and experiment-worthy, or chaotic and in need of rapid stabilization. By viewing hospitals, public health networks, or even a patient's body as complex adaptive systems, managers design policies that encourage information flow, foster decentralized decision-making, and accept iteration as the pathway to resilience and innovation. Now, let's discuss complexity theory. So, complex organizations such as hospitals or public health networks constantly adapt to shifting environments, new regulations, patient demographics, or pandemics because they are composed of self-organizing units, wards, teams, even individual clinicians that sense local conditions and adjust without central orders. Yet every adaptive move carries a degree of unpredictability. A minor protocol tweak in triage can ripple across bed flow, pharmacy demand, and staffing in ways no linear forecast can capture. Change in these systems is therefore nonlinear. Inputs and outputs are not proportional. Feedback loops can amplify or dampen effects, and outcomes often surprise. Over time, the organization's responses have evolved into unique patterns. No two upgrade rollouts or care path redesigns follow precisely the same trajectory, even when they share the same project plan on paper. Embracing complexity theory means shifting from a command and control approach to one of conditions and constraints, designing simple rules, fostering information flow, and watching for emergent solutions rather than prescribing every step, so the system's innate capacity for learning and self-organization can drive resilient, context-specific improvements. In conclusion, health informatics competence rests first on a pyramid of technology-related literacies. Basic reading and numeracy underpin computer fluency and information literacy. Together, they form digital literacy, which, when coupled with health literacy, becomes digital health literacy, the ability of clinicians and patients alike to locate, judge, and apply electronic health information safely. Sound literacies must then be paired with sound theory, because theory provides the mental map that turns raw data and fast-moving change into coherent, evidence-based action. Communication theories such as the Shannon-Weaver model alert us to noise and feedback in data flows, while the data information knowledge-wisdom continuum, expanded by Bloom, Graves, and Nelson, reminds us that data have no clinical value until they are contextualized, learned from, and translated into wise decisions. Systems theory shows that every hospital or public health network is an open system. Inputs are processed into outputs that loop back as feedback, all within a changing context. Complexity theory and the related Cynefin framework demonstrate that such systems behave more like living ecosystems than machines, requiring leaders to match their decision logic, sense, categorize, sense, analyze, probe, sense, or act first to the stability or turbulence of the moment. Change theory then offers a process lens. Kurt Lewin's unfreeze, move, refreeze cycle explains how behaviors shift, while Everett Rogers' diffusion curve clarifies who adopts innovations when and why, spotlighting the crucial role of change agents. At the project level, the Staggers and Nelson spiral lifecycle model guides organizations from analysis and planning through purchase or development, testing, implementation, and long-term evolution, embedding evaluation at every step, so lessons feed the next turn of the spiral. Taken together, these literacies and theories provide a cohesive toolkit. They help designers build usable systems, help managers implement them smoothly, help researchers evaluate their impact, and, most importantly, help providers and patients transform information into better health. Thank you for joining this session. Dr. Cornejo, your videocast speaker. Remember, the literacies and theories we covered, from digital health literacy and the data information knowledge wisdom ladder to systems thinking, complexity science, change theory, and the Staggers and Nelson lifecycle spiral, form a single integrated toolkit for designing, implementing, and evaluating health technology solutions. For a deeper dive and practical examples, be sure to read the excellent Chapter 2 of your textbook, where these models are unpacked in detail and linked to real-world informatics projects.